Hello everybody and welcome back to everythingncea again. Today we will be studying a new physics external wave systems, which is physics 3.3. That's just a quick lesson plan. Take a pause if you want to have a look at that. But today we will be starting with wave phase and standing waves. Now, as you can see in this little bubble here, we will start with a little bit of level 2 recap. If you didn't take physics in level 2, completely fine. I didn't take physics in level 2 and I did it, and I was more than happy going through the standard. It just means there is a little bit of level 2 recap that you have to learn. If you did do physics in level 2, I'd still recommend trying to fill this out yourself, or at least knowing what you'd put in each box, just as a bit of a refresher, because starting a new year, there is some stuff that you forget and that just slips your mind. So we will start with this over here is a transverse wave, and you can kind of think of that as it's just your basic sine wave. It's the wave that you'd most commonly see and that you will most commonly see in this external. And then over here we have the longitudinal wave, which you rarely see in the external, but it's still good to know what it is. And so we'll just quickly start filling in these boxes, because it's just some quite basic standard level 2 stuff that we'll start with. So we're going to be looking at this box first. Now this box and where is it? This box and this box are the same. They're the same answer, and that'll be amplitude. Amplitude is basically the height from the middle or the baseline. The equilibrium position is the correct word there. The height from the equilibrium position to the top of the crest or trough. Now, these two here as well, this box and this box, are the same definition, and that would be wavelength. With the wavelength being the distance from two nodes, I guess would be the best way to think about that. So a wavelength is from the start through to the start again. Now, when we're looking at our calculations in the next couple of slides, we'll go over that a little bit more. But just if you think about it, so that is the start to the start, whereas this one is, if we imagine this bit being the start, if we imagine this trough being the start, it goes all the way up and to the start again, and that is one complete wavelength. Now, if you've heard me talking throughout this, you might be able to guess what this is. This is the trough, which is the place of highest amplitude under the equilibrium position. And this box here, I've already said it. If you don't know, it's the crest, which is the place of maximum amplitude above the equilibrium position. And they are your basic features for a transverse wave. And then we move to the longitudinal wave. We've already covered what this is. This would be the wavelength. So from the start of one wave to the start of another wave, or from the very start of one wave to the very end of the same wave. It's probably a better way to look at it. This little section here is called compression. And that, as you can basically see, is when the waveform is extremely compressed or condensed. That's what that looks like in there. And then rarefaction is this middle bit, where there's the least compression, and that is just called rarefaction. I don't believe that rarefaction and compression is knowledge ever needed in this level 3, but it's still good to know in case it comes up. Just so as a little fact in the back of your head. Now, we'll move on to we'll still do some level 2 recap stuff. Just on some definitions. So, I would recommend, even if you haven't done level 2 or you have done level 2 and this is a little refresher, try and link these words to definitions up on your own. But I'm going to start right now. So if you haven't, pause. If you don't want to, we'll go straight ahead. So we have frequency. Now the definition for frequency here is the rate at which oscillations occur, which pretty self-explanatory. The frequency is the rate in which one complete wavelength is happening. So the more wavelengths in a specific time, the higher the frequency. Second, longitudinal waves, which is the maximum displacement from equilibrium of particles in the medium carrying the wave, which is the waveform down the right we saw on the previous slide. Again, not super relevant knowledge, but still good to know. Next, we have transverse, which will be the maximum amount of perpendicular displacement as measured from the equilibrium position. Again, that's the waveform we saw earlier. A period is the time taken for one oscillation to occur, which is, one wavelength. That's a nice easy one. And wave speed, the speed in which a wave travels. And a super useful formula to know, especially for this standard, is this right here. V equals F lambda. And where V is velocity, F is frequency, and lambda is wavelength. You will need to know and be able to rearrange this equation a lot in this standard. We will cover that, not in this lesson, but in, I think, the next and the coming one after that. This is a super useful formula just to memorize. But now move on to some more level 3 stuff. We'll start looking at phase. So, you can read I'll read the blurb out to the left. Phases, points along a wave undergoing similar motion, are said to be in phase. If a point along a wave is moving in an opposite manner to another point along the wave, those 2 points are said to be exactly out of phase. In phase points are exactly one wavelength or multiples of one apart. Phase difference can be expressed as an angle. Points are in phase or when they have a difference of 0 degrees. To determine if a point is in phase, multiply the wavelength distance between the points by 360. Now, for example, when we look at the points 3 and 5 here, they are exactly half a wavelength apart, as this would be, if we imagine the graph before, this would be the start of a wavelength. So this here is a complete wavelength from 1 to 5. And so half of a wavelength would fall directly down to 3. So we know between 3 and 5 there is half a wavelength. So therefore we would go half times 360 equals 180, which would mean points 3 and 5 have a phase difference of 180 degrees, or they're exactly out of phase. When something is 180 degrees or has a phase difference of 180 degrees, they are exactly out of phase. When we look a bit more in depth in this, 2 waves are said to be in phase if they have the same wavelength and the points on the waves have the same motion. The amplitude of each wave does not have to be the same for the waves to be in phase. So that's meaning the waves don't have to go as high above the equilibrium position to be in phase, which we'll see an example here now. And 2 waves whose wavelengths are identical but have particles moving out of sync are said to be out of phase. If the crests of one wave exactly correspond to the troughs of the other waves, they are said to be exactly out of phase. And we'll have a look at that. So between 1 and 2, they are exactly in phase because point waves 1 and 2, while their amplitude isn't the same, if you follow the wavelength, they are exactly the same, just with different amplitudes. Or they look very similar, just with different amplitudes. So they are exactly in phase. And if you were to times the difference by 360, it equals 0, which we did on the previous slide. Between 1 and 3, this will be out of phase, as waves 1 and 3, you can see it just by looking at it there, their frequency is out of phase. They're not in phase with each other. If you were to multiply the phase difference, it would not be 0. So yeah, that's what out of phase would look like. And then between 1 and 4, this is exactly out of phase, or the final sentence of this blurb, where it says if the crests of one wave exactly correspond to the troughs of the other wave, they are said to be exactly out of phase. So as you can see, the crest and the trough are exactly in exactly the same position for 1 and 4, and they are 180 degrees different. So this is at the very top, this is at the very bottom, which means they are exactly out of phase. The wavelength is the same, it's just exactly out of phase or flips the other direction. I just answered that, but if you didn't catch it, how many degrees are 1 and 4 apart? That would be 180. And then, this is something we'll go into later, but just if you do know, you might have learned it in level 2, you might not have, but if you do know which phenomena would occur at these positions, have a go. If not, I'll go over it briefly now, but more in detail later on. The phenomena that would occur between point 1 and 2, or wave 1 and 2, would be constructive interference, which simply is just when two waves that are in phase with each other constructively interfere to almost create a bigger waveform together. Again, we'll go over that in much detail, but it's when two in-phase waves positively interfere with each other. Whereas at points 1 and 4, as they're exactly out of phase, this would be destructive interference, or where two waves, the best way I'd think about it is two waves negatively interfere with each other to shorten the amplitude of the wavelength for subsequent waves. And so that's really phase for level 3. That's all you really need to know about phase. And then we'll quickly move on to standing waves. So standing waves, which are also known as stationary waves, are produced when two waves with the same amplitude and frequency are traveling in opposite directions. The waves are moving, but when the resultant wave pattern does not appear to be traveling forward, it more appears to look stationary, hence the name stationary wave. Places with the greatest amplitude of oscillation are called antinodes, while where there's zero amplitude of oscillation or complete destructive interference, these are called nodes. So, when thinking about a guitar, you'd have a node at both ends, which would, if I quickly draw it here, you'll have one end of the guitar, second end of the guitar, and you'd have a wave that looks something like this when it's plucked. These are both nodes. These are called nodes as they have zero amplitude. These are fixed points. If this is the equilibrium position, right through there, these would have zero amplitude. Whereas the point with the highest amplitude, this bit right here, there'd also be a waveform down here. And this would also be, this is the antinode. Oh, yeah, this would be the antinode, as these are the places within the stationary wave that have the greatest amplitude. Expanding on that a little more, standing waves, the first harmonic for standing waves would look like this, which is the most basic waveform that can fit inside the length. It has a node at each end and an antinode in the middle, which is what we drew just before. This means that half a full wavelength fits inside the length L. And you can see that with the little formula there, wavelength equals 2L over 1. Now the second harmonic is the next wavelength that fits inside the length, which has 3 nodes and 2 antinodes. This means that a full wavelength fits, this means that one complete wavelength fits inside the length. And then the third harmonic is the third most basic, and then you can read that. You can quickly discern a pattern in between these wavelengths and harmonics, which I would recommend writing down and just finding that pattern, because that's how I find an easy way to think about it. And to have a look about how that will actually be used in an exam question, we'll move on to here. So we have the fourth harmonic here, with the length of this wavelength being 0.54. Now, we have this formula here. Wavelength equals 2L over harmonic number. So this wavelength, which is what we're trying to find, equals 2 times length divided by the harmonic number. Now we know the harmonic number is 4, as this is the fourth harmonic. And we know that the length is 0.54. So all it is now, this will be a formula that you will have to remember for the exam, but I would wait till subsequent videos, as the formula differs slightly depending on fixed ends and stuff like that. But just simply, once we know the fourth harmonic and the length, it's just plugging in numbers. So that is the formula. We know that it's the fourth harmonic, so we substitute 4 for H. We know that the length is 0.54, and we stick that into our calculator. And we now know that this wavelength equals 0.27. And that's just how you'd use it. And then for the fifth harmonic, you plug in the same numbers. This is the formula. What would H be? H would be 5. What would L be? Now this time L would be 1.34, as that's what the question states. And stick it into a calculator. Boom, 0.548. And for standing waves, that is a great bit of starting knowledge. Next time we'll go over resonant frequencies that are fixed at both ends. And I think we might also do ones that are open at both ends. And so that will be using a formula much similar to this. And you will learn that this wavelength differs depending on if there's 2 fixed ends or not. Whereas on a guitar string, as we were talking about before, there are 2 fixed ends, because you have one end of the guitar string and the other, which would make that. Whereas in later on, we'll also get to questions where there's 1 fixed end and 1 non-fixed end, where you get a waveform like that. And you'll also get a question where there's no fixed ends, which will create a waveform. Let me make sure I get this right. I believe like this, with the opposite one that goes through like that, almost looking like DNA. But again, I'll go into that in much more detail later. If you found the slideshow helpful, a free version will be in the comments. Do with it what you need, whatever helps you. More videos will be posted weekly. Hope you enjoyed. Thank you.